On a winter night in the year 1700, the sea came ashore along the Pacific coast of Japan. It flooded fields, it destroyed houses, it set a fire in one town and drove a cargo ship onto rocks in another. And nobody had felt an earthquake. Not a tremor, which, in Japan, is a very strange thing to be able to say. Japanese records of natural disasters go back to roughly the year 600. They are careful, dated, and administrative, the paperwork of a state that took floods and earthquakes seriously. So, the wave was recorded, in detail, in several places, and it did not belong to anything. Scholars later gave it a name, the orphan tsunami. A wave with no parent earthquake. The records survive mainly in what is now Iwate Prefecture, communities such as Sugaruishi, Miyako, and Tsuchi, and their precision is what eventually solved the case. The wave struck on the 8th and 9th days of the 12th month of Genraku 12, which converts to the 27th and 28th of January 1700. From the damage reports, maximum wave heights are estimated in the range of 2 to 5 meters. Not a monster. Not, by Japanese standards, unprecedented. Just inexplicable. At Kuwagasaki, 13 houses were destroyed by flooding, and 20 more in the fire that followed, about 10% of every building in the town. At Tsuchi, 2 buildings and 2 salt kilns were damaged, and fields and paddies were flooded. At Miho, the village headman saw the waves coming and warned everyone to move to higher ground. No damage was reported there. At Nakaminato, a ship carrying 28 tons of rice could not enter port because of the high waves. That evening, a storm drove it onto a rocky shore, killing 2 sailors and destroying the cargo. In the Tanabe area, water flooded wheat fields, rice paddies in a storehouse, and ran up the moat of Tanabe Castle. And here is the detail that tells you these were careful people. Because no one had felt an earthquake, many writers were reluctant to call it a tsunami at all. Some recorded it as merely high tide or high waves. An observer at Kuwagasaki did call it a tsunami. The village headman at Miho wrote down his puzzlement. The waves behaved like a tsunami, but no earthquake had been felt. He was right to be puzzled, and he was right about the waves. The earthquake had happened. It was simply 7,000 kilometers away, on a coastline, where nobody was keeping written records. Off the Pacific coast of North America, about 110 to 160 kilometers offshore, runs a fault called the Cascadia subduction zone. It is 1,000 kilometers long, running from northern Vancouver Island in British Columbia, past Washington and Oregon, to Cape Mendocino in northern California. Along it, the small oceanic plates offshore, the Juan de Fuca and its neighbors, are sliding beneath the much larger North American plate. Ocean crust has been sinking beneath this continent for about 200 million years. It is doing so now, at about 40 millimeters a year. That is roughly the rate your fingernails grow, applied to a slab of the Earth's crust. At shallow depths, down to about 30 kilometers, the 2 plates are locked together by friction. They are not sliding. They are stuck, while the forces driving them keep pushing, which means strain accumulates. The continental edge is being dragged down and squeezed, elastically, like a bent ruler, storing energy that has to go somewhere eventually. And here is what made Cascadia so easy to overlook for so long. Unlike almost every other subduction zone on Earth, it is quiet. It has not produced a megathrust earthquake since the 26th of January, 1700. Other subduction zones rumble constantly. Cascadia mostly does not. For a long time, the reasonable conclusion was that it simply was not that kind of fault. In the 1980s, 2 geophysicists at Caltech, Tom Heaton and Hiru Kanamori, compared quiet Cascadia with the active subduction zones of the Ring of Fire. They found that its structure resembled faults in Chile, in Alaska, and Japan's Nankai Trough, all places known for megathrust earthquakes. Their conclusion was, at the time, met with skepticism, because a megathrust earthquake is the largest thing this planet does. Since 1900, every single earthquake of magnitude 9 or greater has been one. They happen where one plate is forced under another, and the locked contact finally gives way, releasing hundreds of years of stored strain in a few minutes. And because the fault lies under the seafloor moves. A megathrust earthquake displaces a huge area of ocean bottom vertically, which is exactly how you build a tsunami. So the question in the 1980s was simple and unsettling. If Cascadia is that kind of fault, and it has not moved in living memory, where's the evidence of the last time? The evidence turned out to be standing in plain sight all along that coast, dead for nearly 3 centuries. In March 1986, at low tide, a paleogeologist named Brian Atwater was digging along Neah Bay in Washington with a Nijiri-gama, a small Japanese hand hoe. Under a top layer of sand, he uncovered something that should not have been there. Arrowgrass, a marsh plant, still preserved in a layer of old marsh soil. That is a very specific piece of evidence. Marsh plants grow above the tide. Finding them buried under sand means the ground they grew on suddenly dropped below sea level and salt water killed them. And the burial was fast. Fast enough that the sand sealed the plants away from the air, which is why centuries-old vegetation was still recognizable in his hand. The following year, he went up the Copalis River in Washington with David Yamaguchi, who at the time was studying the eruptions of Mount St. Helens. Paddling upriver, they came on a stand of dead gray trees. These are what people call ghost forests. Dead gray stumps left standing after salt water killed them. The obvious explanation was slow sea level rise. The obvious explanation was wrong. The land had not risen slowly to meet the sea. It had dropped by as much as 2 meters during an earthquake, suddenly. And the trees had died where they stood, which gave them a way to date it, because trees keep records. Tree ring dating, dendrochronology, can match the rings of a dead tree against living trees nearby, and read the year it stopped growing. Their first attempt failed. They tested spruce, and the stumps were too rotted to count the outer rings, which are the ones that matter. So, they turned to western red cedar, which resists rot, and compared the dead stumps to living cedars growing meters away on the same riverbank. The dead trees had rings up to the year 1699 and then nothing. Root samples narrowed it further. They died in the winter of 1699 to 1700. Sit with that for a moment. A last growing season, recorded in wood, in the trees themselves, a date, from a coastline with no written records, accurate to a single year. The sand on top of the marsh had a story too. Jody Bourgeois and her team demonstrated that it had been laid down by a tsunami surge, not by an ordinary storm surge. The sea had come in over the land. And this was not one unlucky riverbank. In 1995, an international team led by Alan Nelson of the U.S. Geological Survey added 85 new samples from across the Pacific Northwest. All along British Columbia, Washington and Oregon, the same story. The coast had dropped in a violent earthquake and been covered by sand from the tsunami that followed. Archaeology added its own line. Excavations found evidence of several coastal villages that were flooded and abandoned around 1700. So, by the mid-90s, there was a coastline that had dropped, a tsunami that had come ashore, and a date, the winter of 1699 to 1700. What was missing was the hour. In 1996, the seismologist Kenji Satake connected the two halves of the puzzle across the Pacific. He went to the Japanese annals, the ones that go back to about 600, and found the reports of a tsunami on the coast of Honshu during the Genroku era with no earthquake attached. Converting the Japanese calendar, he placed the waves at around midnight on the 27th to 28th of January 1700. A tsunami takes about 10 hours to cross the Pacific from the Cascadia coast to Honshu. Subtract 10 hours and you get an earthquake at about 9 o'clock in the evening, Pacific time, on the 26th of January 1700. That is an extraordinary sentence. We know the evening and the approximate hour of an earthquake that happened on a coast where nobody wrote anything down, because a clerk in Iwate recorded a strange high tide. The earthquake itself is estimated at moment magnitude 8.7 to 9.2. The plate slipped an average of 20 meters along a fault rupture about 1,000 kilometers long. 20 meters. The Juan de Fuca plate and the North American plate stuck together for centuries, unstuck along 600 miles of contact and moved 20 meters past each other. Along the coast, shaking of that kind lasts not seconds but minutes. Current estimates for the next one are 5 to 7 minutes of strong ground motion. Then the coast dropped, salt water came in over the marshes, and a tsunami went out in both directions, one wave inland across the villages and one west across an ocean. The Pacific Northwest coast had no written records in 1700. It had something else, and for a long time, science did not know what to do with it. Numerous oral traditions describing a great earthquake and an inundation exist among indigenous coastal peoples from British Columbia to Northern California. Virtually all of them have at least one traditional story of an event of unmatched destructive power. In 2005, the seismologist Ruth Ludwin set out to collect and analyze these accounts systematically. Reports from the Huai-At, Maka, Ho, Quileute, Yurok, and Duwamish peoples referred to earthquakes and saltwater floods. Some of the stories carry time markers, a count of generations since the event, and those allowed an estimated date range. Its midpoint was the year 1701. That is a date derived from oral tradition, landing 1 year from a date derived from Japanese tax records and tree rings. It is one of the most striking corroborations in the earth sciences. The Huai-At account of Pachina Bay places the event on a winter evening, shortly after the village's residents had gone to sleep, which matches the reconstructed time of about 9 in the evening. Every community on Tanabe Bay was wiped out, except for Masit, which stood on a mountainside 23 meters above sea level. The only other survivor from Tanabe Bay was a young woman named Anakla Aksop, who happened to be staying that day at Kiek's Inn, on the less affected Barkley Sound. Kwak stories from the north end of Vancouver Island describe a nighttime earthquake that collapsed virtually every house in the community. Powhatan stories tell of a nighttime earthquake causing a landslide that buried an entire village. Macaw stories from Washington describe a great nighttime earthquake in which the only survivors were those who immediately fled inland before the tsunami arrived. The Quileute have a story of a flood so powerful that villagers and their canoes were swept inland all the way to Hood Canal. Accounts from southern Oregon describe a tidal wave that uprooted trees and swept away villages. In those southern accounts, people tied their canoes to treetops, and some canoes were torn loose and swept away. That is a specific, practical, terrible detail. It is what you would actually do. There is also a regional pattern in art and mythology across the whole coast, a great battle between a thunderbird and a whale, along with earthquake-inspired ritual masks and dances. A creature of the sky seizing a creature of the sea and the world shaking. As an account of a subduction earthquake that lifts the ocean, it is not a bad description at all. Not every earthquake story in the region belongs to 1700, and the traditions do not carry calendar dates. But the convergence, oral tradition, Japanese ledgers, tree rings, sand layers, buried marsh soils, is now beyond reasonable doubt. Which leaves the question everyone on that coast now has to live with. 1700 was not the first. How often does this happen? The geological record shows great earthquakes of magnitude 8 or higher along Cascadia about every 500 years on average, with evidence of at least 13 events at intervals from about 300 to 900 years. The average interval across those events is around 570 to 590 years. The last one was 326 years ago. Some subduction zones produce major earthquakes every 1 to 200 years. The longer interval of Cascadia may indicate unusually large stress buildup and therefore unusually large slip when it finally goes. In 2010, geologists put the chance of a magnitude 8.2 or greater event within 50 years at 37%, and gave a 10 to 15% chance that the entire subduction zone ruptures at magnitude 9 or above in the same period. The tsunami produced could reach heights of 24 to 30 meters. That is a wall of water as tall as an 8-story building, arriving on a coast where the warning time is measured in minutes, not hours. Kenneth Murphy, who directed the Federal Emergency Management Agency region covering Oregon, Washington, Idaho, and Alaska, summarized the planning assumption bluntly: everything west of Interstate 5 will be toast. The big cities, Seattle, Portland, Vancouver, Victoria, Tacoma, may be partly sheltered from the full force of the tsunami. Their problem is the shaking. They contain many vulnerable structures, especially bridges and unreinforced brick buildings. One expert has asserted that buildings in Seattle are inadequate even for an event the size of the 1906 San Francisco earthquake. And a magnitude 9 is not the same as a magnitude 8 or a 7? The scale is logarithmic, and the difference in released energy between steps is enormous. There's one more thing about that coastline that most maps do not show. A 2004 study found that a great earthquake would drop the land itself. Cities on the west coast of Vancouver Island, such as Tofino and Ukulele, are at risk of 1 to 2 meters of subsidence relative to sea level. The same thing that killed the cedar trees at Copalis in 1700. The ground goes down and stays down, and the sea moves in permanently. Research continues, and it keeps finding that the zone is more complex than assumed. In 2023, scientists reported a high-pressure, high-temperature seafloor seep off Oregon, the first found on this fault, named Pythia's Oasis, which may play a role in regulating pressure on the plate boundary. But the most striking response to all of this is not scientific. It is what happened when the oral traditions were confirmed. Many indigenous groups in the region began projects to move their coastal communities to higher and safer ground. The Hu'ai-At rebuilt their administration building on a high point in their territory. Whenever a tsunami warning is issued, coastal residents are evacuated to that building, an interim measure, while the longer project of relocating everyone uphill goes on. In 2012, the Quileute secured a land grant from the United States government to move their settlement inland, both against the tsunami threat and because of increasing river flooding. The Shoalwater Bay Indian tribe sought federal funding to move their community uphill, and received a grant to build the first vertical evacuation tower on that coast, completed near the Tokeland Marina in 2022. Think about what that structure represents. It exists because a story told for 300 years turned out to be a hazard assessment. For most of the 20th century, their professional position was that this coast did not produce great earthquakes. The people who lived there had been saying otherwise the entire time, in the only records they kept. And it took a Japanese clerk's note about an inexplicable high tide, a hand hoe in a Washington mudflat, and the rings of a dead cedar tree to make the scientific establishment listen. The fault has been locked and loading for 326 years. The ghost forests are still standing in the marshes, silver and bare, marking exactly how far the water came.